Welcome everyone. In this video lecture, we will think about the Nyquist plot of resistance, capacitance, series combination of resistance and capacitance, and parallel combination of resistance and capacitance. But before the Nyquist plot, we will go for a simple definition of two important things. That is, the first one is our electrochemical impedance spectroscopy, EIS. So basically, the electrochemical impedance spectroscopy, EIS, measures the impedance characteristics of an electrochemical system over a range of frequencies. Basically, we have to measure the impedance over the range of frequencies. Okay, so that's why we are using electrochemical impedance spectroscopy, and Nyquist plot or argon plane or argon diagram, we can say, is the imaginary part of the impedance versus the real part of the system. Okay, so each point in an impedance measurement at different frequencies. Okay, so basically in the Nyquist plot, what we will do that first, before going to the Nyquist plot of resistance and capacitances, we have to generally plot the real part, the x-axis, and in this axis, the y-axis, we can say we have to plot minus z double bar. Okay, so basically, uh, we have to say a impedance function can be written as z dash plus j times of z double dash. Okay, so this one is our real part, of the impedance. Okay, and this one is the imaginary part. Okay, so basically this one is the, suppose any impedance function can be written as a combination of real part plus imaginary part. Okay, this one is j and z double dash. Okay, so real part may be our, simply we can say, the resistive part, and the imaginary part is our reactive part. So I am also writing this part. This one is our, what we can say, resistive part. Resistive resistive what? Okay, resistive part we can say, and this one is our reactive part. So basically, in Nyquist plot, we are generally, we have to plot the real part of the impedance and minus z double dash minus imaginary part of the impedance function, so that we have to plot. Okay, so that we have to think. So first of all, we have to draw the Nyquist plot of resistance. Okay, so first of all, we have to go for the what? Nyquist plot. Nyquist plot of resistance. Okay, so that is very simple, but how we have to think, that I will, means how we have to draw, that I will show you. Okay, so Nyquist plot of resistance. So basically, what it means. So first of all, I am just making a resistance here. Okay, this one is a resistance, and I am writing like this R. So in general, we can write this as a some impedance function. It is R plus J0, because the resistance is there, so there is no imaginary part, so only real part will be there. Okay, so here what we can say, the Z dash term will be only R, and Z double dash will be 0. Is it okay? Means this one is the real part and z double dash will be only 0. So if we have to plot the Nyquist plot, so in the y-axis our minus z double dash, z double dash, and I am saying this one is our z dash. Okay, so z dash is r, so only one number, one finite number we can say. This point will be our one point, that is our r. Okay, so this one for resistance, there is a Nyquist plot of the resistance where there is a only on the real x-axis there is a point say having resistance R, so we have to just put it R. Okay, or simply this part is R or 0, we can say the imaginary part is 0, so you can also write like this R 0 point, and there is no imaginary part. Okay, so there is no need to worry. So this one is a Nyquist plot of the resistance. Okay, now we will go for the Nyquist plot of a, okay, I am writing Nyquist plot capacitance. Nyquist plot of the capacitances. Capacitance, we can say. Okay, I'm highlighting this term. Okay, so first we have to think about the capacitor. So what we will do? Say this one is our one capacitor. Okay, capacitor is C. Okay, so the impedance function of a capacitor can be written as ZC, impedance function 1 by SC. Okay, so this one is the impedance of a capacitor, as we know impedance of a capacitor. So the Z value, so here there is no resistive term. Okay, so the Z dash, Z is generally what we are writing Z dash plus J times of Z double dash. Okay, so here Z dash is 0, there is no this resistive part, plus J into 1 by SC. Okay, or Z plus Z dash, or this one is our Z double dash. So Z double dash we can write 1 by SC. So this can be written as 1 by J omega C. Okay, then to make it imaginary, it should be written as J square. Okay, we are multiplying numerator and denominator by J square omega C. So it should be minus J, because J square is minus 1. So minus J omega C. Okay, so this value is minus J omega C, we can write. So this value simply we can write as 0 minus J omega C. Okay, or you can write it simply minus J omega C means 2 pi C. Okay, this one is the, okay, and one more thing means at DC or lowest possible frequency. Okay, so the capacitor is what, at DC. Okay, it is open circuited and it will offers infinite impedance. Okay, so one thing that I want to write, at DC. Okay, at DC. Okay, capacitor will be open circuited. Capacitor will be open circuited. Open circuited and offers very high impedance. Okay, and just this one for the first part. Okay, clear. Okay. So now SC part is clear. Now capacitor on a, so we have to plot the what, our argon plane. So it should be like minus z dash and z dash. So z dash is 0. Okay. And now this there is a capacitor kind of thing. Capacitor is there. So at high frequency it have 0. So I'm writing two things. At low frequency, at low frequency, okay, at low frequency the z value is more or less, at low frequency or DC it value will be infinite. Okay. And at high frequency the z value will be what, at very high frequency it is sorted, so nearly 0. So we can say that the it will start with this. Okay. And for other one it will go like this for different frequency. Okay. And this one is at low frequency, and bottom one at very high frequency, very high frequency. Okay. In the intermediate frequency it will go like this. So this one is the Nyquist plot for the capacitor one. Okay. Clear this thing? Very simple, means how to plot. Okay. Because at the low frequency, at low frequency, okay, it is just nothing but simply the open circuit rate. Okay. So open circuit rate it have very high impedance. Okay. Impedance, so it is at the high frequency, high. Okay. At the low frequency it is sorted, so it is only 0. So there, and there is no reactive, sorry, resistive part. So there is nothing on the x-axis. Okay. So this one is the simple plot for the capacitance. Now we have to think about the plot of, okay, Nyquist plot of series combination of resistor R and capacitor C. Okay, capacitor C. We have to think about the Nyquist plot of the series combination of resistor and capacitor. So it is very easy. So because we know the above two concept. So for this purpose, what we have to do, first try to make a resistor, okay, and a capacitor which is in the series. Okay. So now the overall impedance we can write as R plus 1 by SC. Yes or no? R plus 1 by SC, or we can write it R plus 1 upon J omega C. Okay, and this can be written as R plus J times of, if we multiply, I am just writing. So this one is R minus J times of omega C. Okay, so directly this can be written as Z dash plus JZ dash. In that form we are generally doing. So here this one is our R, this one is our R. Okay, so it is fixed one. So if we have to plot the This one is our R and capacitor C. Okay, so the vertical axis, that is our minus Z dash, we can write, and this should be our Z dash. Okay, and when at DC, at low frequency, okay, at low frequency, it is somehow start from, okay, mm, or at very high frequency, we can say it will be pass, okay, and the resistance will be only R. So it will be, this distance will be your R. Okay, now above this, it is simply the capacitor kind of thing. So at high frequency it is R, and at the lower frequency it will go R plus something. So it will like this. Is it okay? Very simple. The first component R has to pass all current and considered as an offset. R, the component R, that I am writing, the component R has to pass all current, all current, okay, and consider it an object, and considered as an offset. And then after the capacitor is there, so capacitor, so when it is very high frequency, it is sorted, so it is there only, and at a low frequency it will offer a very high resistance. So I'm like, we can write like this. Okay, so this one for the resistance and capacitor when it is in the series. Okay, so now next, the final one. Okay, now the final one is our Nyquist plot. Okay, I'm writing Nyquist. This one is the basic concept, means to how to think about the resistance, capacitance. Then it will be very helpful for some to know the behavior of some, what we can say, the study of battery and fuel cell, and even the study of behavior around the electrode and electrolytic interface. Okay, so now, so we have to do Nyquist plot of parallel combination of resistor, that is our resistor and capacitor. Okay, capacitor C and resistor R. Okay, clear? Okay, so for this purpose, to think about the Nyquist plot, first I'm just trying to make the, okay, say this one is our resistance, and this one is the capacitor. Okay, okay, this one is our resistor and this one is our capacitor. So here we can say one resistor is there and one capacitor which are in parallel. So we have to plot the Nyquist plot. So before that, we can say the impedance function, the total impedance, overall impedance function is nothing but simply R in parallel with the 1 by SC, or we can say simply R parallel with 1 by J omega C. Okay, so if we solve this one, so this Z can be written as R into 1 by j omega c by R plus 1 by j omega c. So it should be our R by 1 plus j omega c R. Okay. Simply a simple calculation is there. Okay. So here in parallel, so now if we are giving some supply AC signal, okay, in this one, if we are giving some AC signal, okay, so suppose this one is our B T and some current will flow like this. Okay, so first we have to think at very high frequency, the capacitor, okay, I'm writing here. One condition I'm saying at very high frequency, okay, frequency. The capacitor becomes become sorted, and the impedance will be nearly zero, and impedance will be lower. Okay or not? Means impedance will be lower, and at a very low frequency, at a very low frequency or DC, low frequency, or we can say at the DC one. Okay, the resistance, the resistor will comes into picture, comes into picture. Okay, and capacitor will be open circuit, and the capacitor will be open, will be open. Okay, at that time the capacitor will be open. So what happens for if we want to plot for this one, I am just trying to, this axis is our minus z double dash, and this one is our z dash. Okay, so first thing, when there is a low frequency, okay, so at the low frequency it have some r value, okay, like that, it have some maximum value like this r. Okay, and when the frequency will comes into picture at a very high frequency, it is sorted, so it is somehow start from this for high frequency, for very high frequency. Okay, and this one at low frequency, and in between that it will go like this. I will tell how. At certain frequency, say at certain frequency, say f star, it will go up to maximum. Okay, then it will decrease because it's high frequency like this, then below, say this frequency is at f equals to 1 megahertz. So in between that, if we go, it will increase and it will go up to certain, then say this one is our 1 megahertz, so this one is say 100 kilohertz. Okay, then again it will go down like this. Okay, so for resistance and capacitance are in parallel, so the minimum impedance will be zero for high frequency, for very high frequency, and for a low frequency it is r only. Okay, and in between it will follow a semi-circular kind of thing. So in this one is for, okay, and in general, in if we go for some higher level study. So what we observe that the means the Nyquist plot, okay, at the some advanced means we can say the battery cell or something, it will go like this. That will come later. Okay, it will go like this. Okay, this kind of plot will come. So this one will be the high frequency and this curve for the low frequency. This one is the example for means what we can say the battery cell, battery, battery or cell. Okay, the plot. Okay, so it is observed that one notable point is that the at high frequency gives the lower impedance. So one fact that we have to know, high frequency. Okay, I don't have a space, so I am just writing here a notable point that we have to know. At high frequencies, at very high frequency gives lower impedance, lower impedance, lower impedance, and low frequencies frequencies are uh, going to provide much more impedance. Okay, this one is the some concept that we have to know. Okay, I'm highlighting this one with okay, yellow color I will use. Okay, so this is all about this simple Nyquist plot diagram, and this one is for very high means what we can say example for even for the uh, biomedical circuit modeling. This kind of Nyquist plot will come where the combination is like maybe combination of like R and RC kind of three thing for with parallel one. Okay, means even for the fractional one also in this kind of curve Nyquist curve or Nyquist plot we can observe. So this one is for your RC. Okay, similarly for the capacitor R and C, when this is series it is like this. For the capacitor it is simple, it will follow on the, it will go on the y axis. And for the resistance one it is very simple, it will just nothing but simply it will on the real axis. Okay, will be on the real axis. Okay, so this is all about this lecture. Okay, so thank you for watching this video. Thank you.